So here we're going to go over these problems that relate to properties related to carboxylic acids. In this first question, we're trying to identify ones with higher boiling points. Our first one compares an alcohol, which we know has hydrogen bonding for the OH group, with the carboxylic acid, which not only has hydrogen bonding in the OH group, but also has a second dipole-dipole interaction from the carbonyl. And so because of that, the carboxylic acid is going to have a stronger attraction and therefore a higher boiling point. In part B, we have a carboxylic acid versus an ester. They both have the carbonyl in common, but the carboxylic acid has the OH group, which allows for hydrogen bonding, while with the extra oxygen carbon bond in the ester, there is no hydrogen bonding available here at all. Since there's no hydrogen bonding there, that means we don't have as strong an attraction, and the carboxylic acid will have a higher boiling point. Part C, we have a pair of carboxylic acids, and if we look carefully at the number of carbons that are attached, we see that they're the same. Both of them have 6 carbons attached. So now it becomes a question of how those carbons are arranged. And we know that straight chains are generally able to pack better than branched chains. And so the unbranched molecule will have better van der Waals attraction between the chains, and therefore a higher boiling point. And in part D, we have a diacid, which is going to have much stronger attraction than a monocarboxylic acid. Water solubility based on intermolecular forces. Now we know that carboxylic acids that have short chains, such as acetic acid on the right, are going to be much more water soluble than a carboxylic acid with a long chain. The longer the chain gets, the more nonpolar the molecule gets. In part C, we actually have 2 equivalent length chains. The difference is one of them is the salt. It's the deprotonated form. It's an ionic compound. And that's much more polar, much more soluble than the protonated form. And in part B, we have an alcohol versus a ketone. Alcohol with hydrogen bonding, stronger attraction, more polar than a ketone. In question 3, we're looking at predicting the product from acid-base reactions. So we know that carboxylic acids are acidic, and with an appropriately strong base, such as sodium hydroxide, we can remove that and form the ionic compound, the carboxylate salt pictured here. And that's what's going to happen in any of these, regardless of what the carboxylic acid is that we'll remove that proton and form an oxygen anion. Alright, our final question on here is to rank compounds on the basis of increasing pKa. So 1 for the lowest pKa. So 1 is going to be our strongest acid, and 4 for our weakest acid. So what's changing here is the group that's attached to the carboxylic acid. We have both electron withdrawing groups for most of these, and then in part B we'll see we have an electron donating group. Remember, the key with acidity is the more withdrawing the group is, the more it increases acidity. So something like fluorine, which is a highly electronegative element, is very electron withdrawing. And that does a much better job of increasing acidity as opposed to something that's much less electronegative like iodine. And so in this first question, they just rank on the basis of the more electronegative the group is, the stronger the acid. Part B is largely the same question. Fluorine, chlorine, hydrogen is the substituent, and then silicon. The reason that silicon is the weakest acid or the highest pKa is that silicon, which is found below carbon on the periodic table, is an electron donating group. And so if electron withdrawing groups are able to increase acidity, then electron donating groups have the opposite effect and will decrease acidity.